This is section 5.4 and 5.5 together. More trigonometric formulas. Now, this is actually a one-part lesson. We're doing something unprecedented, two different sections in only one part. Um, and there's a good reason for this, so I just want to explain that first. What we're going to be doing in this lesson is deriving some trigonometric formulas. And these formulas, they're not really that important for this class, but they are somewhat important for calculus. And I say somewhat because even in calculus, you won't see the formulas that we derive today that often. But it's good if you have some exposure to these formulas today so that when you encounter them in calculus, it's not a big surprise. This lesson is not so easy. All right, and it's also not so short. So we're kind of finishing off with a bang. You could say this lesson is a doozy. People don't even use that word anymore. I remember when I was in grade school, they would. At least one teacher used to say it all the time. She said, "Oh boy, this one's a doozy," meaning it was hard or long or difficult or whatever. Well, this lesson is a doozy. All right, so without further ado, let us begin our doozy lesson. Sum and difference formulas. Now, there are several different forms of the sum and difference formulas, and so I'm going to put those up first on the screen. And as you can see, they're not the easiest formulas to memorize. And so here's another bit of good news. You do not have to memorize any of the formulas that are in this lesson. All right, today's lesson is all about deriving formulas. It's about analytical trigonometry, which is, not using graphs or visual applications, but just looking at the mathematical nature of the trig functions. But as I said already, you do not have to memorize any of these formulas. However, I do expect you to write down everything that's on the screens, which is the same as for all lessons. All right, so besides noticing that these four formulas are not easy to memorize, you probably look at them and say, wow, that looks kind of like a mess. And actually, it is kind of a mess, but the proof is interesting. And so let's look at the proof. All right, so we're going to consider two angles, alpha and beta. It doesn't matter what you call your angles, U, V, X, Y. Well, here we're calling them alpha and beta. If you want, you could say that alpha is like U and beta is like V. It doesn't matter. The distance d in the following two unit circles are equal. Don't be confused by this one, which I'm circling now with a mouse arrow. This one just indicates that you're on a unit circle. The radius is 1. And the same is true of this one over here that I'm now circling. This one simply indicates that we're on a unit circle. Now let's carefully look at these diagrams. Okay, on purpose, we're not picking a specific beta or a specific alpha, but we are picking an alpha. In this case, this alpha is obtuse, and this beta is acute. It doesn't have to be for the formula to work. It's just convenient for this proof. All right, so let's look at this left-hand diagram first. If we look at this left-hand diagram, we can see that there's this angle beta here and the angle alpha, and there's also a point that this ray of beta connects to, and that point has an x-coordinate of cosine beta and a y-coordinate of sine beta. That's nothing new. You know that from the unit circle. Any point on a unit circle has an x-coordinate, that is the cosine of the corresponding angle, and a y-coordinate, that's the sine. Now the same is true of this other point, cosine alpha, sine alpha. It's just an x and y coordinate. Now let's look over here to the right-hand diagram. And the thing that is not so intuitive about these diagrams, but is confirmable just by observation, is the fact that d equals d. All right, so You can kind of tell by looking at it. I know it's cheesy to say you can tell by looking at it, but this is one case where telling by looking at it is actually pretty valid because these are both unit circles of the same exact dimensions. So if this inscribed triangle over here looks like it's the same size as the inscribed triangle over here, well, it probably is. And actually it is. I'm just saying that the fact that they look similar helps to understand. All right, well, think of this. We see this inscribed triangle over here. It looks like a Dorito chip. All right, well, think of this inscribed triangle as just being rolled over. Okay, it's being rolled over clockwise. So we have it here now in this position, and we're going to roll it over clockwise until its base coincides with the positive x-axis. And that's exactly what we have in the right-hand diagram. We have that inscribed triangle rolled over so that its base coincides with the positive x-axis. All right, now the other thing to keep in mind about this, and this is even more important than the rolling thing, is where this angle alpha minus beta comes from. Now we have to go back to the left-hand diagram for that. You can see that there's this angle alpha, it's obtuse. We can also see there's this acute angle beta. Well, how do you find this angle that I am tracing now with the mouse arrow, back and forth? This angle that I'm tracing is not alpha, and it's not beta, but it's given by alpha minus beta. This is the angle alpha minus beta. And when we roll it so that the base coincides with the positive x-axis, we still have the angle alpha minus beta. And that's essential to understanding this proof. Now, looking at this right-hand diagram a little bit more, we still have points on the unit circle. This point up here has an x-coordinate of cosine alpha minus beta, just as you would expect, and a y-coordinate of sine alpha minus beta, just as you would expect. This point down here is even easier. It's simply the point 1, 0, 1, 0, because it's on the unit circle. Okay, next key step. From the first one, that is the left-hand diagram, we obtain d equals square root cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared. That's simply the distance formula. You've seen it plenty of times. It just comes from the Pythagorean theorem. It's the distance formula to express d in the left-hand diagram as square root cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared. From the second diagram, that's the right-hand diagram, from the second one we obtain d equals square root cosine alpha minus beta minus 1 squared plus sine alpha minus beta minus 0 squared. Again, we're just using the distance formula. Just to jog your memory, remember the distance formula is d equals square root of y2 minus y1 squared plus x2 minus x1 squared. You can also invert them, where d equals square root of x2 minus x1 squared plus y2 minus y1 squared. It doesn't matter the order. All that matters is that you're taking a difference of x-coordinates and a difference of y-coordinates, and you're squaring them and then square rooting the sum of those squares. There's nothing new about the distance formula. All right, now our next step, and again, this is the importance of writing down everything on the screens, because what I'm about to talk about refers directly to what's on the previous screen that you diligently wrote down. All right, well, the next step is we know that d equals d, and so d squared must equal d squared. And now that makes it easier for us because we get rid of those big radical signs. And so we just square each of those d's and we end up with cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared equals cosine alpha minus beta minus 1 squared plus sine alpha minus beta minus 0 squared. All right, now here comes the tedious algebraic and arithmetic chugging through numbers part. All right, and if you ever have to do a proof like this in college, you know, the main thing is just be careful, write everything out, don't rush and try to skip steps. I know that some of you like to skip steps, not write a lot, but the only way to handle calculus and other courses higher than calculus is You need to be systematic. It's just the only way. Mathematical talent and ability does not cut it. You also have to be, on top of that, you also have to be systematic. And while I'm on that, and I won't digress too far, don't worry about it, it is possible, believe it or not, even if you don't have mathematical talent, to be very systematic and still be able to get by. All right, so that should, if you think of yourself as not a math person, and yet you might still have to take um, math in college, even if you don't plan on being an engineer. Well, be systematic. That's the key. Be systematic in everything. Oh, and one last thing, and you'll forgive me because this is the last video, so I am allowing myself the liberty of digressing a little bit. Uh, this whole course that we've been doing, which we call pre-calculus, also has other names. It's sometimes called advanced math. Sometimes it's called college algebra. And the interesting thing about that second title, college algebra, is that sure enough, there are colleges where this course is a requirement. And in fact, last year I tutored a college student, who was taking college algebra as a requirement for her major, and she was not a math major. This was one of her core requirements. And it turned out that the college algebra course that she needed for graduation coincided with something that she had taken in high school that was called pre-calculus. And yet, she needed the tutoring because, she wasn't really used to being that systematic. All right, enough of my digressions. Now, you can see that this big long line here is really just a matter of plugging through. Cosine alpha minus cosine beta squared gives you cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta plus sine squared alpha minus 2 sine alpha sine beta. Okay, all this, there's no point in explaining every step because it's just algebra. There's nothing more to it. It's just algebra 1, and it's tedious but necessary. All right, now we group all those terms together because thanks to our trig identities, cosine squared alpha plus sine squared alpha is 1, and so that's going to help us simplify things. So we group terms in order to capitalize on that. And look at the next step. Boom. Look at how short it gets. Why? Because cosine squared alpha plus sine squared alpha is 1. And so this part over here, I'll use my nice little red pen. This part over here simply reduces to 1. And this part over here simply reduces to 1. And then this whole beast over here, which looks ugly, simply reduces to 1. Right? That's the whole beauty of this. So we end up with this shorter line. And now look, it gets even better. Boom. Okay? Because look at the pattern here. 2 minus 2, a bunch of stuff, equals 2 minus 2, a bunch of stuff. And therefore, one bunch of stuff equals the other bunch of stuff, and that's why we have cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. All right, the next formula of cosine alpha plus beta is actually simple because all you do is use your result from the first proof, the first part of the proof, and you replace it with negative beta because you know that alpha minus negative beta is the same as alpha plus beta. And then when you simply put negative beta instead of beta into what we just proved, you end up with cosine alpha cosine beta minus sine alpha sine beta, and that is the formula for cosine alpha plus beta. Okay, now let's look at the sine sum and difference formulas. So the first thing we're going to do is we're going to replace alpha with pi over 2 minus alpha. Now, this often confuses students because they're like, what the heck? We just proved this for alpha. How can you just throw a monkey wrench in there and put a pi over 2 minus alpha? Well, you need to think about this carefully. This pi over 2 minus alpha is just an angle. That's all it is. It's nothing more than an angle. Okay, so once you've proven the formulas as we have for cosine alpha minus beta and for cosine alpha plus beta, you can use those formulas freely. And so you can think of this cosine alpha plus beta or cosine alpha minus beta. I'm just going to circle this little portion here. You can think of this cosine alpha minus beta in simple terms as cosine one angle minus another angle. Cosine one angle minus another angle. And since this guy here, that we already circled in red, is simply an angle, then this guy here is really just cosine one angle minus another angle. Or if you like, cosine one angle plus another angle. It doesn't matter which form you use. It still comes out. All right, so we have cosine pi over 2 minus alpha plus beta equals cosine pi over 2 minus alpha cosine beta minus sine pi over 2 minus alpha sine beta. Notice that all we did here is we used this formula here, okay? We used this formula here, and we replaced alpha with pi over 2 minus alpha. We replaced alpha with pi over 2 minus alpha. So this is where we can use identities that we've learned. Remember how on the top of the screen, one of the Pythagorean identities saved us a lot of space? Well, now we have to use the cofunction identities. The cofunction identities tell us that the trig function of an angle equals that trig's cofunction, that trig function's cofunction complement. All right, so it means that if we have, for example, 20 degrees, and we're looking at the sine of 20 degrees, we know that the sine of 20 degrees is the same as the cosine of 70 degrees. Think right? Co-function. The co-function of sine is cosine. The co-function of secant is cosecant. The co-function of tangent is cotangent. All right? All the cofunctions show this pattern. All right, so if the cofunction identities are true, then we know that sine pi over 2 minus alpha equals cosine alpha. We know that cosine pi over 2 minus alpha equals sine alpha. And we know that cosine pi over 2 minus alpha minus beta, which is just an angle. Alpha minus beta is nothing but an angle. Just looks complicated, but it's nothing but an angle. Then cosine pi over 2 minus alpha minus beta equals sine alpha minus beta. All right, beating a dead horse into the ground, but again, you'll forgive me because this is the last lesson. The sine of an angle is the cosine of that angle's complement. The cosine of an angle is the sine of that angle's complement. All right, so we can conclude from the cofunction identities that sine alpha minus beta, notice that we have replaced we've replaced one of these expressions, this expression here that was circled, we've replaced it with what we found, which is this guy here. And so sine alpha minus beta equals sine alpha, and this cosine pi over 2 minus alpha just becomes sine alpha because of cofunction identities. Sine alpha cosine beta minus cosine alpha sine beta. Okay, the last proof for the sum and difference formulas. We replace beta with negative beta, as we did before, and we obtain sine alpha minus negative beta equals sine alpha cosine negative beta, etc. And that simplifies to sine alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. All right, that was some pretty intense proving. The good news is that all the rest of the proofs in this section are not as tedious as these, although they still are a bit tedious. Sum and difference formulas continued. Here's another sum and difference formula. We've seen the sine ones and the cosine ones. Here are the tangent ones. Tangent u plus v equals tan u plus tan v over 1 minus tan u tan v, and tangent u minus v equals tan u minus tan v over 1 plus tan u tan v. The proof is actually quite simple based on all that hard work we did on the last screen. And now we're using a quotient identity. Tangent u plus v equals sine u plus v over cosine u plus v. It's just the quotient identity. And now we can plug in everything that we proved. Sine u plus v is the same as sine u cos v plus cos u sine v, and cosine u plus v is the same as cos u cos v minus sine u sine v. Now, here is a step that is not intuitive. You can see that doing this gives you an equal result, because you're doing the same thing to the same exact thing to the numerator as you are to the denominator. You're dividing by the same thing. And so you know that when you cross multiply, those will end up canceling and you end up with the same original fraction. All right, well, we know that that's true, but the thought of throwing that cosine u cosine v in there is something that's not intuitive, and something that is done merely for the sake of convenience. Not because you have to do it, but because you want to do it, because it's going to help you simplify in a convenient way. And we'll see why it's convenient in just a second. This whole thing simplifies to tan u plus v equals tan u plus tan v over 1 minus tan u tan v. All right, well, you don't just have to take my word for it. Let's look at these two parts, right? Okay, right now I'm circling with the mouse arrow just a certain portion of this numerator, because since it's plus something, we can split it up into two fractions in the numerator. The first fraction would be sine u cos v over cos u cos v, and the cos v's cancel, and you end up with sine u over cos u, and that's just the same as tan u. Now, if we look at these two over here, we've got cos u sine v over cos u cos v. Well, the cos u's cancel this time, and we're left with sine v over cos v, and that's the same as tan v. All right, and you do similar down here. You've got cos u cos v, that just simplifies to 1, and then you're left with minus sine u sine v over cos u cos v, and that is the same as tangent u tangent v. All right, double angle formulas. Sine 2u equals 2 sine u cos u. Cos 2u equals cos squared u minus sine squared u, which also equals 2 cos squared u minus 1, which also equals 1 minus 2 sine squared u. Okay, now the thing about this formula here is that all of these are valid forms of the cosine 2u formula. They're equally valid forms. It's not that you simplify until you get the last line. No, each one of these lines is a valid form of cosine 2u. All right, the proofs are actually quite simple. Let's start with sine 2u. Sine 2u is the same as sine u plus u, and then we can just use the sum and difference formulas that we already have proven, and we get sine u cos u plus cos u sine u, and that is the same as 2 sine u cos u. Notice here that this sine u cos u is not in the same order as cos u sine u, but since multiplication is commutative, it doesn't matter. So we end up with 2 sine u cos u. Cos u plus u is the same as cos 2u, and that, using the sum and difference formulas, gives us cos u minus sine u, and that is the same as cos squared u minus sine squared u. And these other forms up here that I circled in red are really just consequences of the Pythagorean identities. All right, so you know that sine squared u is the same exact thing as 1 minus cosine squared u. When you replace sine squared u with 1 minus cosine squared u, you end up with this 2 cosine squared u minus 1. And when you replace cosine squared u with 1 minus sine squared u, you end up with 1 minus 2 sine squared u. Double angle formulas continue. Tan 2u equals 2 tan u over 1 minus tan squared u. Okay, let's prove that. And we're going to do it the same way. All right, so this is a chance for you to use your skills. And using a similar method to what we did on the last screen, I'd like you to prove that tan u equals 2 tan u over 1 minus tan squared u. Pause the video, try to do this on your own, and then resume when you have an answer. Okay, so as you probably figured out, tan 2u is the same as tan u plus u, and then we can use the sum and difference formulas that we already proved. Tan u plus tan u over 1 minus tan u, and that's the same as 2 tan u over 1 minus tan squared u. Power reducing formulas. Now, you definitely will see these in calculus. So write them down. Sine squared u equals 1 minus cosine 2u over 2. Cosine squared u equals 1 plus cosine 2u over 2. Tan squared u equals 1 minus cosine 2u over 1 plus cosine 2u. All right, so what's the point of these formulas? Well, you see they're called power reducing because instead of a squared term on the left, you end up with non-squared. And that's going to help you when you're doing integrals in calculus. Again, don't worry about memorizing these formulas. Even in calculus, you're probably not going to have to memorize them. But there will be problems that require use of them where the formula is given to you. In any case, let's go through the proof. Cosine 2u equals 1 minus 2 sine squared u. Okay, this is one of the results that we found on the last screen, right, when we were figuring out the double angle formulas. And you'll see that cosine 2u equals 1 minus 2 sine squared u is one of the valid forms for the cosine 2u double angle formula. Well, now we can try to solve for sine squared u. So we move that over and we get 2 sine squared u equals 1 minus cosine 2u. Therefore, sine squared u equals 1 minus cosine 2u over 2. And that is the first power reducing formula. Now the second power reducing formula, cosine 2u equals 2 cosine squared u minus 1. Again, that's one of the valid forms for the cosine 2u double angle formula that we already proved. Solving now for cosine squared u, we proceed with algebra 1 steps and we get cosine 2u plus 1 over 2 equals cosine squared u. So we've proven 2 of the power reducing formulas. Now look in the upper right corner and we're going to prove the third. Actually, false alarm. Look at the bottom of the screen and I just kind of spelled out that one more step that was lacking. Since cosine 2u plus 1 is the same as 1 plus cosine 2u, that last line there at the bottom of the screen shows explicitly how we've proven that cosine squared u equals 1 plus cosine 2u over 2. Okay, now you can look at the upper right portion of the screen. So tan squared u equals sine squared u over cosine squared u. We know that simply from the quotient identity, the quotient trig identity. And so I can now use what I've already proved earlier in the screen, and I can use the sine squared u power reducing formula and the cosine squared u power reducing formula, replace them with these, 1 minus cosine 2u over 2 divided by 1 plus cosine 2u over 2, and I end up with tan squared u equals 1 minus cosine 2u over 1 plus cosine 2u. Half-angle formulas. All right, let's derive these. Well, first, the half-angle formula is sine u over 2 equals plus or minus root 1 minus cosine u over 2. The cosine u over 2 equals plus or minus root 1 plus cosine u over 2. And the signs of sine u over 2 and cosine u over 2 depend on the quadrant in which u over 2 lies. That's why it's plus and minus. And finally, tan u over 2 equals 1 minus cosine u over sine u, which also equals sine u over 1 plus cosine u. All right, now just a quick question in case you're curious, besides the fact that these are consequences of the mathematical nature of trig, you might say, well, what on earth are you ever going to need this for? And the answer is that sometimes it's nice to find the exact value of a sine. For example, let's say that you wanted to find the exact value of 15 degrees. Now, if you plug sine 15 degrees in your calculator, you'll get a bunch of decimal places, but you know, that's really just an estimation. If you want to get a really exact value, as exact as you possibly can be, then actually the only way to really do that is using a half-angle formula. Okay, because 15 degrees is half of 30, and so you can use this. You can use this formula because it will allow you to express everything in radicals and not use decimal places. All right, now some of you probably weren't even curious about that, and you know the fact is you don't have to worry about it because, like I said, these formulas really aren't used that often, and even when they are used in calculus, you'll probably be given them to refer to. So don't worry about memorizing them now. All right, the proofs. Sine squared u equals 1 minus cosine 2u over 2. That's something we proved from the last screen. Notice how everything builds on the last thing. Math is so much like a building. You have to lay the foundations and then you keep building and building and building on top, but every level depends on the previous level. All right, sine squared u equals 1 minus cosine 2u over 2. Let us now replace u with u over 2. We can do that because u over 2 is an angle, just like u is an angle, just like z is an angle, just like u divided by 6 billion is an angle. All right, it doesn't matter. You can replace u with u over 2 because you know that the first line of this proof is true. So you end up with sine squared u over 2 equals 1 minus cosine 2 u over 2. And that simplifies to sine u over 2 equals plus or minus root 1 minus cosine u over 2. All right, so we just took the square root of both sides and we simplified that 2u over 2 to just u. Okay, now let's see if you're ready for another challenge. I would like you to prove the cosine u over 2 equals plus or minus square root 1 plus cosine u over 2 formula. I'd like you to prove that now based on what we just saw for the proof of the first formula. Pause the video, try to do that on your own using a similar strategy, and resume when you have an answer. Okay, so you should have come up with this. Cosine squared u equals 1 plus cosine 2u over 2. We proved that in the last screen. Cosine squared u over 2 equals 1 plus cosine 2u over 2 equals over 2. And then that simplifies to cosine u over 2 equals plus or minus square root 1 plus cosine u over 2. Okay, and now the tangent half-angle formula. Tangent squared u equals 1 minus cosine 2u over 1 plus cosine 2u. All right, this is just from the last screen. It's the power reducing formula for the tangent. All right, and then we proceed. We simply replace u with u over 2. And finally, we end up with tan u over 2 equals plus or minus square root 1 minus cosine u over 1 plus cosine u. Now, those who are observant among you will see that what we end up with in the lower right portion of the screen is not what we set out to prove. Okay, well, that's because the proof is not done yet, and it's going to be continued on the next screen. Okay, so this is what we ended up with on the bottom right-hand portion of the last screen. Tan u over 2 equals plus or minus square root 1 minus cosine u over 1 plus cosine u. Okay, so there are two things we can do with this now. I'm going to do part of it on the left and part of it on the right. First on the left. Tan u over 2 equals plus or minus 1 minus cosine u over 1 plus cosine u times 1 minus cosine u over 1 minus cosine u. All right, when you see this beastly expression, right, you might tend to freak out and say, oh my gosh, what is going on? But if you really look at it, you know, what I just circled in red is just 1. That's all it is. It's just 1. 1. It's the number 1. All it is the number 1. 1 minus cosine u over 1 minus cosine u, because anything over itself is 1. And so we are not changing this mathematically, but the reason we're throwing this in is because it's going to help us to simplify, as we will soon see. Tan u over 2 equals plus or minus square root of 1 minus cosine u squared over 1 minus cosine squared u. Now, this stuff downstairs here in the denominator, 1 plus cosine u times 1 minus cosine u, is a difference of squares, and so it's the same as 1 minus cosine squared u. And, of course, the numerator up here, 1 minus cosine u squared, is just another way of writing 1 minus cosine u times 1 minus cosine u. Now, where does this get us? Well, tan u over 2 equals plus or minus square root 1 minus cosine u squared over sine squared u. And we simply replaced 1 minus cosine squared u with sine squared u because of the Pythagorean trig identity. And finally, we can now get the square root of the numerator and of the denominator, and we end up with tan u over 2 equals 1 minus cosine u over sine u. Okay, your last challenge, or your last video challenge, we still have another class, of course, but your last homework video challenge is going to be to prove the other part of the tan u over 2 half angle formula. Right? 1 minus cosine u over sine u is one part of it, but as you know, there's another equivalent expression. I'd like you to prove that now. So pause the video, try to do that using the same technique and strategy as on the left-hand side of the screen. And you're now going to try to prove the other part of the tan u over 2 half angle formula. Pause the video, try and do that on your own, and then resume when you have an answer. Okay, so similar steps. Tan u over 2 equals plus or minus the square root of 1 minus cosine u over 1 plus cosine u times 1 plus cosine u over 1 plus cosine u. Tan u over 2 equals plus or minus square root 1 minus cosine squared u over 1 plus cosine u squared. Tan u over 2 equals plus or minus square root sine squared u over 1 plus cosine u squared. Again, all we did was use the Pythagorean trig identity. Finally, tan u over 2 equals sine u over 1 plus cosine u. Okay, no more proofs, but hang on because the video is not over and you need to write these down. Product to sum formulas, product to sum formulas. Again, they look rather beastly. Sine u sine v equals 1/2 cosine u minus v minus. All right, I know they look beastly, but be patient, write them down exactly as they appear. And we're not going to do the proof right now. We're going to do it a bit later. But I want you to write these down. Product to sum formulas. When you've written them down completely, you can go on to the next screen. Sum to product formulas. Sine u plus sine v equals 2 sine u plus v over 2 cosine u minus v over 2 and all the rest. You're starting out with a sum or a difference on the left-hand side, and you end up with a product on the right-hand side. So write these down exactly as well. Sum to product formulas. When you're done writing them down, you can proceed to the next screen. Okay, we finally reached the end of it. That was a long video, and it's been a long year. And you've now earned the right to say that you've completed all the videos for this class. The classwork, we will prove the product to sum and sum to product formulas. Anyone who can do it without help will receive 5 points of extra credit on the final exam. Okay, so those formulas on the 2 previous screens that you have faithfully written down, you're going to try to prove them on your own. And don't think you can't do it, because you can. All right, so see you in the next class.